Chapter 2, Making Predictions. We can return to our two models that we set up in Chapter 1. The first one is I of t equals 10e to the 0.231t. That was our exponential model. We had 10 initial infections, and it was tripling or doubling every 3 days. So in 3 days, we'd have 20. 6 days, we'd have 40, et cetera, and that gave us this model. We had a similar pattern with our logistic growth model, where we had, initially we had 10 infections. Initially it was doubling every 3 days, but we had a maximum infected population of 10,000, and that gave us our logistic growth model. The whole idea of producing these models is to predict the future, or at least tell something about the future. In this case, let's suppose we go with our exponential model and we want to know how many infections there are in 120 days, roughly 4 months. We can plug 120 in for t and compute this E button. Most calculators have an ln and an e to the x button. So you'll activate this with the second ln button. And by pre-calculus, I assume you're pretty literate at doing this computation. So plug that number in and compute what happens. We end up with 1.09 times 10 to the 13 infections. That's almost 11 trillion. That's outrageous. We only have 7 billion people on planet Earth. That's more than 1,000 times the number of people on Earth. So obviously, this exponential growth function goes wrong. In the logistic model, we have I of t as 10,000, 1 plus, etc. And if we plug 120 in for t, you can compute this on your calculator. We end up with 9,999.99. It turns out we're very close to this ceiling population of 10,000. We're as close as we'll get. You could plug in I of 10 million days, and we'd still have 9,999, just a bunch more nines here. We approach this without ever reaching it, and we definitely never exceed it. So you can see this function works. This is actually a decay term right here. And we call it a transient term, actually. As t approaches infinity, this term goes away. This is an exponential decay term. This decays to 0. 0 times 999 is 0. And it gets closer and closer to 10,000 over 1 plus negligible, which is 10,000. So differential equations, this is pretty important when we study various natural phenomena that come about in physics and mechanical and electrical engineering. We're interested in the long-term steady-state behavior of these solutions. The long-term steady-state behavior here is we're tending toward 10,000. This transient term disappears, essentially. Here's a simple graph. This 10,000 is a horizontal asymptote. That's our maximum population. Exponential growth just takes off to infinity and beyond. And logistic, well, it follows that. That's what's called a logistic S-curve. Lots of applications for logistic curves and population studies. Sometimes populations in the wild will reach a maximum, what's called a carrying capacity. And also in marketing, if we're marketing something, there's a maximum market saturation. For instance, for marketing insulin, we're limited by how many diabetics we have. I doubt the drug companies could peddle insulin to non-diabetic people, although it wouldn't surprise me. And so this S-curve, if you're an investor, you want to get in down here. Once we pass this inflection point, you can still make money in the company, but most of the money is to be made back here. So we could also turn this around. I'm not going to go through it in this video, but given a number of infections, you could always plug in here and solve for t. You could take this, if you want to do it as an exercise, plug 1.09 times 10 to the 13 in here, solve for t, you should get approximately 120 days. It won't come out exact because we rounded this off. Same thing over here. If you plug in 9999.99 in here for I and solve for t, you should get about 120 days. So although you have to keep a lot of significant figures here, it's easy for these days to wash out if you drop too many sig figs here, too many decimal places. But that's useful math. In pre-calculus, it's good to be able to manipulate these exponential expressions, because if you're taking a tech class or an engineering class or a chemistry or a physics, they'll just assume that you can manipulate these things and solve for various variables. That's the takeaway you want to have in pre-calculus. So, okay, that's all for this. We'll be back. Chapter 3, we're going to talk about what engine drives logistic growth. We're going to look at the logistic growth from an arithmetic fashion, and that will give you an idea of why this produces the S-curve. And it's pretty important, chapter 3, because also we're getting closer and closer to the SIR method, the susceptible, infected, recovered model. A lot of work we're doing here will make that SIR model very intuitive, very easy to understand. Our goal is for you to be able to not just plug into the SIR model, but to understand what all the various terms are when we do the calculations, to give you a thorough understanding of what's going on. And chapter 3 is really the beginning of that. We'll be back with that video shortly.